Hello students, now let's move on to next theorem. If f belongs to R of alpha and c is a positive constant, then f belongs to R of c alpha. And also integral a to b f d c alpha is equal to c into integral a to b f d alpha. So we need to prove this in the second part of the theorem. So now let's get into the proof. Given f belongs to R of alpha, then by the condition of integrability for any epsilon positive, there exists partition P such that u of p comma f comma alpha minus L of p comma f comma alpha is less than epsilon by c. And instead of epsilon, we have written epsilon by c, and you will come to know why in the upcoming steps. Okay, name this as equation 1. And now consider the upper sum of f with respect to c alpha and p. So according to the definition of upper sum, it is equal to summation I equal to 1 to n capital Mi into delta alpha I. Instead of delta alpha I, we have delta c alpha I, where c is a positive constant. Now let's find what is this delta c alpha I. Okay, see, now consider delta c alpha I. So according to the definition, we have c alpha xi minus c into alpha xi minus 1, because delta alpha I is alpha xi minus 1, and therefore delta c alpha I will be c into alpha xi minus c into alpha xi minus 1. And if you take the c outside, you are left with delta alpha I, which is nothing but alpha xi minus 1. And here, instead of delta c alpha I will just write c into delta alpha I. So I can also take the c outside the summation, as this has nothing to do with this summation. So c into summation I equal to 1 to n mi delta alpha I. Therefore, u of p comma f comma c alpha is equal to c into u of p comma f comma alpha. Name this as equation 2. Similarly, L of p comma f comma c alpha is equal to c into L of p comma f comma alpha. Okay, so 2 minus 3. 2 minus 3 implies u of p comma f comma c alpha minus L of p comma f comma c alpha is equal to c into, see here, c is common in both the terms. So I can take the c outside and write u of p comma f comma alpha minus L of p comma f comma alpha. And we know that this term is less than epsilon by c. So this term is now less than epsilon by c into c. Okay, so at last you have f belongs to R of c alpha. Why? Because this term, this difference between upper sum and lower sum of f with respect to c alpha is less than epsilon. Therefore, f belongs to R of c alpha. And this is all about the first part of the theorem. And now moving on to the second part. To prove that integral a to b f d c alpha is equal to c into integral a to b f d alpha. So here, since f belongs to R of c alpha, we have this integral equal to the upper Riemann integral. So integral a to b f d c alpha is equal to upper Riemann integral of f with respect to c alpha. According to the definition of upper Riemann integral, that is equal to infimum of u of p comma f comma c alpha, where p is any partition of closed interval ab. Okay, and see here, since c is positive constant, I can take this outside and I can write c into u of p comma f comma alpha, where p is again any partition of closed interval ab. And also I can take this outside here and write c into infimum of u of p comma f comma alpha. Why? Because c is again a positive constant. So C into infimum of u of p comma f comma alpha, where p is any partition of closed interval a comma b. And here, according to the definition, this infimum of u of p comma f comma alpha is nothing but the upper integral of f with respect to alpha, with this c here. So c into upper Riemann integral of f with respect to alpha. But since f belongs to R of alpha, we can write integral a to b f d alpha in place of upper Riemann integral. So this is all about the second part of the theorem. Thank you.